Okay, today we started talking about open channel flow, and the basic setup is what I'm showing on the upper left of the screen here, where we have a channel slope that's fixed at alpha, alpha being the angle with the horizontal, and for small angles, alpha that's approximately sine alpha, approximately tangent alpha, or the channel slope S naught. And then we think about the depth of the channel, and I'm defining the depth here as y. So going from point 1 to point 2, we go from depth y1 to depth y2. At any point along our channel, the velocity is given by the volumetric flow rate q divided by width divided by depth. All right, now for this setup, we can write down our energy equation going from 1 to 2 as dropping the pressure terms, since at the top of the water column pressure is atmospheric. The position in the vertical is y1 plus the change in the channel slope, S0 times L, where L is the distance from 1 to 2, plus V1 squared over 2G is equal to Y2 plus V2 squared over 2G plus the head loss due to friction. So this is all assuming steady flow. If we further constrain the analysis and take our energy equation and consider uniform flow means Y1 equals Y2, and therefore V1 equals V2, and we're assuming that W is a constant width. Then this the energy equation reduces to the statement that the channel slope has to be balanced by the frictional loss, or channel slope is equal to frictional loss over per distance, which we defined as the friction slope, S sub f. Now, how do we go about formulating the friction slope? Well, we could do it with the Darcy-Weisbach equation. Darcy-Weisbach equation would tell us that S sub f is equal to F 1 over 4 times the hydraulic radius, where the hydraulic radius is the area divided by perimeter, V squared over 2G. That's the Darcy-Weisbach approach. That gives us an equation that relates velocity and channel slope. If we set this equal to S naught, then we can solve for velocity as the square root of 8G over F RH S naught. Now we talked a little about the Chezy equation. Chezy equation replaces this coefficient of square root of 8G over F with C. But really what gets used is the Manning equation. And Manning's equation notes that this coefficient, the friction coefficient, which here is 1 over F, still has a little bit of dependence on the depth through RH. So the Manning equation replaces that friction coefficient with what's known as the Manning coefficient, which is defined as n. So the velocity is 1 over n, then the hydraulic radius to the 2/3 power and channel slope to the 1/2. Where I should note that RH is equal to the cross-sectional area divided by the wetted perimeter. And please look at the complete lecture notes for the definitions of those components. This Manning's equation, written in this way, is for SI units. In English units, the factor of 1 in the numerator here becomes 1.49 for English units. But this is the easier one to remember, obviously. What we have then is a relationship between the velocity, the depth, and the channel slope, related through this friction coefficient and Manning's n, which is tabulated for different types of channels. We'll pick up with this analysis on Wednesday, and then start to talk about how flow varies away from this when the channel slope changes or when there's other components of the channel that forces it away from uniform conditions.